And Alexander is going to talk to us about Sprints, a machine learning ecosystem for forecasting solar-driven events and scientific event crowdsourcing. So I'll give you a 5-minute warning, when you have 5 minutes left and in your own time.
Brilliant, thank you. So I wish I could be there. Unfortunately, I had a conflict with the Space Weather Workshop. And I'd like to thank really the organizers for this opportunity. And apologies, my voice. I should have gone to that conference because maybe I wouldn't have gotten sick. So bear with me with my voice and all of that. So again, thank you. And should I share my screen
Yes,
or how?
please, if you have it there handy.
Copy. Okay, stand by. Thank you.
Okay, we see that.
Okay. Let me see how big I can make it.
You might be able to do a full screen as well.
Sorry, I never work from PDF. Enter full screen. There we are.
Perfect.
Okay, wonderful. So thanks again. This is on sprints. If you're curious, the opportunity in which this project was executed was under a NASA SBIR program, and that was transferred to the Air Force. And we recently completed a few months ago. So with that, the sprints framework key takeaways. Well, what is it? Really envisioned to be an ecosystem for collaborative and repeatable space weather data processes, science and forecasting. Why? At least in part, to streamline space weather applications, machine learning applications in particular. I will give some examples for in a bit later on. From technology readiness levels, TRLs 1 through 4, higher to proving grounds and test beds. And if folks in the room have been following what's going on in the United States for proving grounds and test beds, the proving ground example would be the CCMC, and a test bed example would be NOAA SWIPSI. So what is it comprised of? Well, like any online system, really, it has APIs, a database, widgets, a collaborative ecosystem like Jupyter Lab, for instance, has external catalogs, and this I'll get into some detail about. But really, that is such a critical thing, I think, for this field, especially as we look to do machine learning and other such things that require start and end times of events, event associations, also for validation and verification purposes of your model. If you have a Jupyter Lab type of environment, you can do data fusion. You conveniently can use those APIs to retrieve those catalogs, whether they're flare catalogs, radio burst catalogs, start and end times, whether there are catalogs that have those associations of flares to SEPs, so solar energetic particles. Everybody there's knowledgeable there, I'm sure. Shocks, CMEs, and so the idea is we really want to try to align some of this stuff, and you need to do data fusion to do that. Machine learning processes, we want to be able to explore, develop, validate, and deploy these models, really ideally. As I'll get in a little bit more detail, there's a lot of one-offs out there. It's been said sort of a GitHub graveyard. GitHub is great, but how do we actually put machine learning into a runtime ecosystem where everybody can see, like maybe there's a leaderboard for real-time sort of testing of these models and things like that. There are additional libraries out there. I've listed some of the Python libraries, perhaps that some of you all aware of, SunPy, PySat, Komodo, PlasmaPy. There are lots of wonderful libraries out there, and again, these can just be simply imported via your kernel, or they can be a stable type of environment in which your team can do execution. And so that's another part of the vision. If you have a project to do something like this, you can get your team working collaboratively online in the cloud no longer bringing data down to yourself on your local laptop, wherever you may work, but you are bringing you and your team potentially to work collaboratively in this ecosystem. And then there's the AWS GovCloud, which we use because, again, it was a Department of Defense effort. So security was important for us. So, but it really could be any cloud environment, whatever you prefer. So those are the key takeaways here. We'll keep going. So an architecture diagram, a logical architecture diagram. There's a lot going on in this picture. I'll break it down in maybe just a couple of minutes. And we'll start with the top left because I'm generally focused on making things operational, see how things work. So on the top left, you have your operational data coming in from NOAA. Again, this in real time, NOAA SWPC, NOAA NESDIS. You have your ingestion scripts. Hey, I want to be reading in real time GOES, proton, electron, X-ray data, GOES ACE discover data. And then you have these event detection scripts that can determine the start and end time. We have our own capability. We've also used others' capabilities. For instance, the latest events pipeline from Lockheed Martin. So for instance, if you're curious, getting into the weeds immediately right away, but some important weeds, I think, if you have a real-time system and you want to predict solar energetic particles, you generally need to know where the active region is, where that solar eruption went off that is potentially associated with a solar energetic particle. And so Lockheed has their latest events pipeline with a flare detector that tells you where that flare went off. So we do use others. The system is really meant to be interoperable and extensible to other capabilities that exist. We're really not looking to do everything, but looking really to play well with others, of course. So just following that arrow, and then we'll pick up some of the other ones along the way. It goes into your timescale database, Postgres database here. It can support those catalogs I referred to earlier. And also you have your underlying measurements database there as well. And just in case I forgot to include it later, forgive me, a little foggy, but the database covers GOES data from 1986 through present, and GOES ACE Discover, ACE and Discover 1997 through present. And I do want to mention the importance, if you do work in the cloud, if you work with big data visualizations, cloud optimized data formats are a great tool. So if you are unaware of Parquet formats or ZAR formats and you work in Python, I highly encourage you to take a look at those data formats. We are recently wrapping up a project for NASA working with Anaconda, the leading company to do Python open source type of capabilities. And then you can also have hosted data, and that's meant to be that little data silo there, and really can support things such as any data like from the Punch mission, for instance. And that database can all be accessed if you write a Python API. And again, if you want to bring in new data into the system, writing the API is not too bad. So you can extend the data set. Again, our foundational data set, what I like to call GOES ACE Discover, can be easily extended to radio burst data and other things like that, and you just go from there. So there you have your Jupyter Hub ecosystem where you can do your Python notebooks. From there, you can do these Bouquet servers. Bouquet is a way of doing dashboarding visualizations. You can deploy your models in that way. And if you have Jupyter Hub, you can perform the data fusion. You can do the machine learning applications. And again, I'll get into a specific configuration, if you will, of Sprints that is really meant to do the machine learning runtime for it. And then on the top, you have all these wonderful Python libraries. Towards the left, you have more of the HELIOPHYSICS type of specific libraries. And then on the right, you have more of the big data type of libraries that Python has as well. Just to clean up the rest here, make sure I cover the basis here. You can have on the left, you can have model data wherever it may come from. You can have heliophysics data from other locations, whether it's the JSOC or whatnot, and then metadata from the HEC, from sharps, or from others. So again, not meant to be exhaustive by any means, but that's sort of, again, meant to be extensible data sets that you can bring into the ecosystem. So everybody is doing the same thing. Data preparation does not need to be hopefully reinvented every time. I think when we submit proposals, just a general comment here, when we submit proposal, yes, our science question may be different, but truly a lot of times we're doing the same data preparation. So if we can save that, and data preparation really all the way from data wrangling, identifying where the data is, to doing some data fusing that may include some visualization and things like that. Anaconda has performed some surveys of data scientists in the field, and generally speaking, that's 66% of the work. So if we can save some 66% of the work, you're able to focus more on the science, and we're of course saving money, or using that money for really getting into other things rather than data access, wrangling, data preparation, normalization, and things like that. And then just to wrap it up, on the right there, you have your code repositories, GitHub, Bitbucket, and then you have your users. Again, more focused for us, at least for how we develop the architecture and ecosystem to be used by several folks. So operators coming in and testing it out, looking at it, even though really at the end of the day, whatever comes out of this, whether it's a flare forecast capability, a SEP forecast capability, can be deployed to their own environment. It provides sort of like a mini proving ground, if you will, not dissimilar from what CCMC intends their cloud ecosystem to be. And then scientist education really could be a great tool for students as well, because as we know, heliophysics, with the interdisciplinary field that we are, our data is everywhere. Okay, so here are the requirements that we had to do for this project. We were focused on SEP forecasting. The data sets, again, GOES, ACE, Discover, we wanted to be foundational in that. It's a data-driven approach. So we wanted to sort of build from there, 1986 through present. That's pretty good. That's getting on 40 years now, which is pretty wild to think. But the primary objective was to predict these AFRL, Air Force Research Lab, SEP forecast requirements. So the list there is 10 MeV at 10 PFU, 10 MeV at 40 PFU, etc., all the way to 100 MeV at 1 PFU. And you can see a diagram there. They really wanted the forecast almost provided in time series. Time series in this case was every 6 hours. You can see gaps there. I won't get into it, but really that came from initial requirements that they tried to gather at a high level. So we were going after this to forecast out in the future. Okay, so the data and the solar events here on the right, I'm sure on the left, people generally get the concept. I find these cartoons generally helpful if you're talking to some folks that are unfamiliar with what you're referring to. Screen went black. Okay, good. Okay, but on the right is one of these bouquet dashboards. If you recall, I said bouquet server. Bouquet server right here, right? So this is an example of it. Unfortunately, I don't have it pulled up right now. Otherwise, I'd give you guys a mini demonstration. But suffice to say that here are these are the foundational data products I was referring to before. You have your flare detections on the top here. You're viewing about, I guess, 8 days or so. These are the Halloween storms. And you can see the start and end times of these flares based on the automated detection algorithm. You can see the same thing for the solar energetic particles in the middle plot. And then on the bottom plot, you can see your solar wind structures, whether they may be shocks, CME sheaths, or things like that. And then in the database, there are catalogs that have event associations. So in red there, you have that flare that is associated with that event, that solar energetic particle event in the middle plot. And then I've just highlighted the CME sheath in below. But what you're able to do here, and what's envisioned, we haven't done this because we were more focused on getting the solar energetic particle forecasting going with the machine learning approaches that we were looking at, you can do version control on these catalogs. You can come in and say, no, I don't agree with Alec here that this flare is associated to this solar energetic particle event. So you can go in and with your username, basically using version control, Git, and all that stuff, control the start and end time and correct these events. Correct the start and end time. You can disassociate these events and then reassociate them. One of the big challenges, I think, is that we're all we may be using GOES, ACE, Discover, and things like that, but there are primary, secondary instruments on GOES, primary, secondary satellites, GOES. And so what are we supposed to be using? There's some rules that you can follow. So if you have rule-based type of stuff in your database, but really ideally we should be using the same data, the same event association. So we're all comparing apples to apples. So just an example there of what the dashboard looks like, but this is highly interactive. I did mention briefly those optimized cloud formats before. You can view, I don't have the example pulled up here, but you can view an entire year of GOES, X-ray, long, short, GOES, protons, 1 through 100 MeV channel, and then ACE, Discover, whatever you're viewing, an entire year of that. So that's basically 1-minute cadence data sets and 5-minute cadence data sets for the most part, but 1 minute, let's call it. Those can be visualized in under 2 or 3 seconds, right? So you're talking about being able to view the entire solar cycle, or let's just say our data set, 1986 through present, in about 5 to 10 minutes. So you can just go through it and visualize it and see these event relationships, right? Zoom in, zoom out, and things like that. So I'm a very visual guy. I like the ability to interrogate my data. And again, when your tool is set up so you can do annotations on your time series and then separately annotations on imagery stuff, now I think you're really cooking. That is a key component for data preparation for any machine learning project. Okay, so how is Sprints used for SEP forecasting? Well, the data is findable, accessible, interoperable, and reproducible. So fair. So maybe some of you guys have heard that. So the idea is that it's analysis and ML ready. The machine learning workflows make it possible to have a new model and deploy it within 1 to 2 days. So if I go and tell my machine learning engineer, hey, Brianna, I just corrected, or somebody else just corrected 5 events, whether it was start and end time, whether it was event associations, she can rerun her notebook and she has a new neural network in a matter of minutes. And then we go through our pipeline. If some of you are familiar with Agile DevSecOps or CI/CD, continuous integration, continuous development. So I work with a software engineer company. So I've picked up some of this language and processes along the way. It can be redeployed in your operational environment in case our quote proving grounds, next gen proving grounds, in limited time. So you're talking about it's a great turnover type of deal, right? So efficiency. And you can deploy those forecasts into the integrated user customizable dashboards and have machine-to-machine products. So on the right, there's just some visualizations that I really like to see. So obviously you can see the solar cycle. If you're looking at blue, those are the flare events that, at least in our catalog, and again, we used other catalogs to help us get started, whether it was Noah Swipsy's or others in academia. We sort of took a look at them and used the visualizations to help along the way. But blues, circles, blue lines there on the parallel coordinate plots. I love parallel coordinate plots. If you don't know what they are, check them out. So blue events not associated to SEPs, and then the green to red, those are your flares that have been associated to your SEP events there as well. And then the parallel coordinate plots, so you can see the 3 solar cycles, and then the parallel coordinate plots, it's hard to see here, but you have parameters that you may want to investigate to do your machine learning training, such as the long and the short ratio of the flare, the decay phase of the flare, where the flare went off, longitude, the flare peak, and then the fluence of the flare as well in the last parameter. Okay, so data curation process here. I'm going to pick up the pace a little bit here. So data curation process here, you can just see some examples of what your catalog may look like. So you have your different IDs, you have your start and end times here, you have your latitude, longitude. Ideally, every flare in your database has a latitude, longitude associated with that. In reality, we know that's a real challenge, but of course you want to do as much as possible. You can go in and enter this information into the data table and update your flares. Perhaps you have additional information, whether it's imagery or otherwise, and you're convinced or you have a good idea of where that flare went off. And then just a Python notebook of how you would use the Sprints APIs, a Python notebook on how you would write your own APIs if you ingested your own data set like radio burst. Okay, so just going to keep going. It doesn't get any simpler than a multi-layer perceptron model in terms of a neural network. So the flare parameters that we put into this guy was X-ray peak flux, X-ray fluence, X-ray peak ratio, and flare longitude. All right, so these were the results. So on the left here are the AFRL requirements, 10 MeV at 10 PFU, etc. The SEPs here, we trained on 163 of them. We tested on 18 of them. We did iterate this quite a bit. So there was K-fold validation that was associated with this. And then on the right, you have your skill scores that we achieved, the model achieved. Hideki skill score there, so 0.58 for 10 MeV at 10 PFU. That seems to be like a fairly competitive, also fairly typical where the field is at in terms of state of the art. There are probably some models out there that may be able to do a little bit better. And then your probability of detection of 0.56 or 56%, and then your false alarm ratio of 34%. You can see the other results there. You'll notice like, hey, Alec, you got false alarm rate of 0 for 50 MeV and 50 MeV at 10 PFU and 100 MeV at 1 PFU. We think that some of these SEP events, right, the way if you get a really big flare, it may be very well easier to predict some of these higher energy events, spectra related SEP events. But it was a pretty robust validation. Again, I'm not a machine learning person. This was done by somebody with a master's in machine learning. I'm merely the subject matter, bringing her the necessary information so she can do the process. Okay, so these are the CCMC SEP Challenge result events, or all clears on the left here. These are all the SEP Challenge events that CCMC has put forth to the community. These were completely withheld as well. So you had these events, so train and tested. Furthermore, we tested on these additional 11 events. So if you really know what we tested on, it was 29 events because we withheld even more holdout events for the CCMC challenge events. So the dates on the left, I don't know why, but whenever you see black here, it should have been green. Red means we didn't get the forecast correctly, but it's great. It's a probabilistic model. That's why in part machine learning is so fantastic for several things like operations and forecasting. But you can see our model. This is presenting the 10 MeV at 10 PFU within the first 24 hours, and then the 100 MeV at 1 PFU for the next 24 hours. And you have your thresholds respectively, at least set for optimizing the skill scores at 56% and 26% respectively. And you can see everything in black is good, so it means everything we got correct. Everything in red we got wrong. And so I just want to put out an example like, hey, 22%, we gave a false negative. But recall that the threshold is at 26%. So it's still very useful for forecasts or anybody to see that 22%, even though we base our skill scores on that threshold. You can see the visualizations on the right. We actually do have the forecast outputted onto the real measurements themselves. The horizontal black lines are for the 10 MeV at 10 PFU. It's a double y-axis. So you have the probability on the right there for which these events to occur, and then your horizontal purple lines are for the 100 MeV at 1 PFU, and we just give a couple of examples. The bottom one was a tough one. It was an event that barely went over 10 PFU. but nonetheless, it's really good to visualize how your forecast does in overlapped, overplotted with the measurements themselves, or however you may consider it. All right, so we're almost there. I see I have maybe I'm going to take 5 more minutes, and then we can move on to any potential discussions or questions. But what are we doing with this SEP model? Well, it's running real time on the CCMC scoreboard. You can go ahead and check it out if you'd like with the other, I think, 7 models that they have running in real time there. We're considering changing the model, so it's not extending out beyond 24 hours. It's another model that's slightly more robust than actually what I showed you here. And then we really want to develop a time series machine learn model. There are other specific requirements that we've seen from the DoD to do some of this information. And we want to explore options for end users to access the Sprints dashboard. This could mean transitioning Sprints framework ecosystem to other locations such as NASA HelioCloud. So it's a little bit more extensible and there's more room to grow potentially. Maybe there's a bigger footprint of users for folks like NASA HelioCloud, not dissimilar from ESA's data labs. All right, so cataloged information drives data discovery. So I talked about this before, but again, to me, this is totally worth emphasizing. So and I'm going to read this, apologies. Catalog scientific information is often defined by spatiotemporal and additional quantitative attributes. There are many scientific disciplines that rely upon cataloged information or events to do science and achieve data discovery. Examples, climate, you got wildfires, droughts, tornadoes, El Nino, La Nina. Space weather, we already covered that. Socioeconomic impacts, power grids, supply chains. A lot of this stuff is defined with dates and times and things like that. And if you have underlying data sets, you really want to define those types of things. But what is the overall problem? Cataloged information is often disparate, conflicting, and difficult to apply data formats, like journal tables. Like, okay, you have a catalog of SEP events in a journal table. Really hard to virtualize that, or just a pain, right? And then transcription errors and all that stuff. So that hinders sort of the process. That enters into that 66% of data preparation I was talking about earlier, which is a pain. Your approach, at least my thinking, create community open source tools, crowdsource catalogs, centralize and versioning of cataloged information, employ practices for acceptance, version criteria, whoever that may be. Maybe it's a group of folks of SMEs that understand this stuff, and they get together once a month and they look at all the updates coming from the community and they accept, reject accordingly. Or you just keep multiple versions of catalogs because people have different definitions for different reasons, whether it's operations, science, or what have you. Goals: define catalogs and events by applying community standards, enable effective database queries and data downloads, and focus a scientific question and drive efficient data discovery. Okay, so example, space weather events. I already did this, but here it's written out a little bit more concretely. So I'm going to go ahead on to the next page because I do want to give you guys time on the clock here for discussion or just time on the clock. All right. What else? What else can you use this type of platform for? I alluded to it at the beginning. So a machine learning platform for space weather. For what it's worth, this is what we do at NextGen for the DoD. We've developed a weather machine learning platform in which we basically take a similar ecosystem to Sprints in terms of data preparation, where scientists and SMEs can come in. But there's more to it if you really want to create a ML ecosystem. So wonderful. So this is the slide with the most text, so please bear with me. So space weather data-driven events, ML approaches have been shown to outperform statistical and physics-based approaches in many settings. I talked to Enrico. He was at the Enrico Camparale. He was at the space weather workshop. He said he gave a presentation. So you may see some similar language since he and I are working on proposing such a machine learning platform for the community. ML results in the literature have historically been difficult to reproduce. challenging to evaluate for potential transition to testbed operations. Move towards an open approach is a must, where code and data can be made publicly available to ensure reproducibility. Not just talking about GitHub here. Each of the repository provides its own pipeline for transforming data, training a model, performing prediction, and evaluating a model. This process of building out a pipeline for each problem is costly, time-consuming, and leads to results that are not reproducible and not easily comparable against like algorithms. So what is needed for the community? You really need a one-stop shop for space weather ML needs. Enable teams to develop ML applications at scale by providing tools and techniques, allow rapid implementation and evaluations of new models. Thank you for letting me read. Sorry. Thank you. So here are all the ML algorithms. Here are some of the ML algorithms. Perhaps some of you in the room are authors of these algorithms here, but you got flare prediction, segmentation, CME, time of arrival, solar wind classification, magnetosphere classification, solar wind velocity, DST. All of these things are out there. All of these deserve, I think, to be in an runtime ecosystem for machine learning. All of them have code, as you can see by the hyperlinks there, and some of them have data, which is also ideal. All right, I'm running out of time, but we need to scale these ML algorithms that the community is putting up. We need to get away from working on your local laptops. They need to put into a system where we can do that. So a unified platform, bottom line, take home message for y'all. A unified platform and pipeline will accelerate the advancement of AI and ML across a variety of domain areas in space weather. Here's what it looks like. I'm not going to spend time on it. Again, we use sprints to a degree here. Sprints entire ecosystem is on the bottom left, that little block there. The machine learning platform, that's everything on the right that you care about in terms of running your machine learn model. Transforms, evaluators, doing the training, validation, refinement, and then your deployment into real-time operations. And then also having a scoreboard, not dissimilar from what CCMC has. And then your model, your algorithms are coming in from the top left. All right, other ecosystems, I already mentioned Helio Cloud could be a good place for the community to gather around to do this sort of stuff, ESA Data Labs. And I'll just leave this up. Conclusions, how do we unify? It's not easy. So thank you all very much. Do appreciate the time.
Thank you so much. Have we any questions here in the live audience first? I think, yeah, one down the back.
Thank you. Very nice talk. I'm from Astronomy. We work on something similar. I mean, at least we are interested in something like that. So I'm wondering, how do you deal with when you have like pipelines that can run for processing the data also for days? Do you have like some kind of, I don't know, support for like common workflow language or other kind of workflows that takes a lot of time?
Yeah, so if you there are multiple things that could take time. So I guess you're not specifically talking about ML training, but perhaps just the pipeline building. Can you clarify a little bit, like what?
So sometimes you have to pre-process the images to obtain actually images, right? And then start the training afterwards. And that could be time consuming, and you don't want it to do it on Jupyter Notebook.
Right, copy, yeah. And yeah, it doesn't all have to be done in Jupyter Notebook. You can certainly in the cloud have your Python script routines do that. So less of maybe the collaborative environment, but you would have more of more of a deployment of these scripts that would do the pre-processing in the background. You could potentially, you know, if I'm coming in there, I know there's this pre-processing capability, but I just need to run that script. Right, so that can all be configured in doing that. And then there are these sort of pipelines in which you can execute that. We haven't done that type of pre-processing. That can be big, and I do understand that those are compute resources that you need to be aware of when you're executing anything in the cloud. But you can I'm not saying you have to do everything in the cloud. You can have a hybrid approach where you need to do the data pre-processing on a HPC type of environment, and then persist that data into the cloud so your team can see it. So there are certain things, yeah, that are glossed over here. So it's a very good point that pre-processing does deserve. It's sort of like, hey, it's not just kick off a notebook and then you got something running in the background. It's probably something a little bit more involved there for sure.
Can I also ask another question?
Yeah, I think so.
Based about so you're using AWS, which is for us turned out to be very costly to store data. What's your experience with that? Like, even
yeah, so so for all the data, right, and that's another reason why I really liked working with the time series data. Wasn't too bad, but for all the data 1986 through present and then 1997 through present, it's about $500 a month for us to run this system, and maybe it's a little over 500 gigabytes. When you're talking about imagery, and we do this for the Air Force all the time, we work in terabyte land, you know, as I'm sure a lot of you may with SDO data and things like that. So it is costly. And again, this questionnaire, how do we unify? In my mind, this is a NASA Helio Cloud. They should be supporting the infrastructure. Your individual research projects should be accounting for some of this material, right? If we're saving time, at least in theory, on data preparation, data wrangling, and it's not costing as much to do that stuff, some of that cost can be put forth to the cloud ecosystem to provide you greater efficiencies. But it is extremely costly. We've been there on projects before where I have my boss look at a bill for $5,000 and go, Alec, what happened? And I was like, well, we fused some data and we had to do some stuff. So, I mean, I don't know what you want, but this is what we decided to go learn about. So it's definitely a learning experience. But looking to NASA, ESA, others to support some of the costs there, find that more efficient balance there for data preparation, so we can be more efficient in working the science side. So it's a balance. Yeah.
Anybody else here in the room? I might take an opportunity here. You mentioned that, I guess, the user base should be pretty broad between forecasters and scientists and everything in between. Do you think that some people will be more hesitant to move towards like working in the cloud, people who are very attached to their own laptop, or what? Do you have any thoughts on that?
Yeah, we've already had experience with that. I know the Helio Cloud folks have experience with that. And actually it was related to the previous question on cost. They didn't know how much it would cost to, for instance, download data to their local because they may need to use it, like they've created a video or something like that. But it is, we tried to get users to get on the ecosystem and use it in a similar way. I think to some degree there needs to be a push to do it. It depends on who you get. Is it going to be old thought, like there's no way, I'm just set in my ways, leave me alone type of personality, or is there a convenience type of mechanism in there where, hey, this just isn't the workflow I am used to, and that exists as well. So they're sort of being stubborn. They're sort of like, I'm not used to this type of capability. In my opinion, you need to draw some folks in with some fundamental tools. And for me, that bouquet server type of thing, where you have these type of plots where you make it exceedingly easy for the user to do this data fusion process, and you lay it out in a notebook, basically give them zero excuses to tell you why. Like if I have a teammate says, hey, I'm going to do this on there. Why? Well, I think it's more efficient. I want to understand why they think it's more efficient, because as a PI or as a co-I, as a project, you know, that the efficiency is number one for me in terms of getting towards the science, answering the science question that we've laid out. So it's a great question. We've had issues on our projects before. In some ways, NextGen is lucky because we force our people, right? Lack of a better words, but we basically see you have to work in the cloud. But when you have a co-I, right, you don't have that sort of perhaps authority over them. They're kind of like, I'm just going to do my science on my local laptop. So it's another great question. I think it's something that the community is going to struggle with. But again, if you can provide them with clear examples, use cases, workflows that are on the cloud that they can follow, streamlined, then at least you have something to back up your argument for why they should not be working on their local.
Thank you. Yeah, I think that's about all the time we have for questions. So let's thank our speaker again. That was really great.
Thank you, guys.